Okay. Hi, welcome to today's session. We have two virtual talks in the morning. The first one is given by Mark Lalage from INRIA. He will tell us some new results about the graph alignment problem. Please, Mark.
Okay. Thank you for for the invitation to this very nice workshop. I'm very sad I couldn't make it to the US. I hope next time I will be in Berkeley to meet. So I will present a new algorithm for the graph alignment problem. This is joint work with Luca Ganasali, who is a PhD student finishing his thesis with Laurent and myself. And the last part will be a work done with Waïs Azizan, who is a student at ENS. So do not hesitate to interrupt me whenever something is unclear. Okay, it's not working. Okay, it's working. So I will present the problem of alignment of graphs and start with a few pictures. Since I think I'm the first to speak about this problem in the workshop, but there are many experts in the audience. So you start from the graph 1 on the left, put indices on the vertices or label, and then you perturb a little bit the graph by adding or removing a few edges. You obtain the graph on the right here, with not the same layout as the graph 1 here. So you remove indices on the vertex on the graph 2, and your task is now to recover the original label, the indices of the vertices on this graph 2. And you have only access to the two graphs in terms of nodes on the edges. So to give an example, here is a result given by an algorithm I will present at the very end of this talk, where I'm drawing the answer given by my algorithm here on graph 2, here on graph 1, but you see I did not change the layout of the nodes, so you see that a few edges are appearing or disappearing. Now in green, I have vertices for which I was able to make the good prediction in terms of its index, and in red, like these two here, I made a mistake. So if you look at the mistake that I made, since here my algorithm is returning a permutation of the indices, each time you are making a wrong guess, this means that you are swapping two nodes, like these two guys, or you are creating a cycle, so you are taking the wrong index for this one to this one, and this one, and this one. So you only have cycles on matching as a result as errors, which are possible here. And again, in green, you have, if you want, self-loop, so nodes for which the prediction is good. So here, what I'm doing is I'm superposing the two graphs, so graph 1 and graph 2, and I'm coloring in different colors the different edges. So you have green edges belonging to both graph 1 and graph 2. And you have orange and blue edges corresponding to the added and removed edges, so which are not present, either present only in graph 1 or either present only in graph 2. So here I'm just plotting the match edges found by my algorithm. So these are the edges which are between two match vertex. But you see that sometimes I'm able to match also edges between a wrong prediction and a good one. Okay. So this green, and you see that all the edges are green, so belonging to the intersection of graph 1 and graph 2. Here I'm plotting the mismatched edges, so where I'm making an error. And you see that I'm making error on noisy edges, so orange and blue one, but also on a few green vertices, edges, sorry, belonging to the intersection graph. So if something is unclear, again, do not hesitate to interrupt me, since I have no feedback at all I cannot see your face, it's hard to see whether you're following or not. So here, what I'm plotting are only the noisy edges, so edges which belong to one graph but not to both. And you see that each time I have a wrong match, so I'm making the wrong prediction for a given node. This is mainly due to the fact that there are a lot of incident noisy edges, so edges which do not belong to the two graphs, which are incident to this red wrong prediction. So this is it for the problem. And now I will present theoretical results obtained with Luca and Laurent. And for this, here I did not specify at all a model for my graph for the noise or anything. So I will start with defining my model, which is so-called correlated Erdős-Rényi model. So some of you are familiar with this model, but I will at least recall the notation for my talk here. So you will have the two graphs G and G prime on the same set of nodes, let's say. So n is the number of nodes. And you will put edges randomly with two colors, whether it's blue if it belongs to G and red if it belongs to G prime. So here is a small picture, give an example. And now the probability to get two color edges will be lambda times S divided by N. So lambda and S are the two parameters you will need to remember during the whole talk. So for example, the edges between node 3 and 4 is both blue and red. This is two color edges. And now you put single monochromatic edges, either blue or red, with the probability lambda times 1 minus S divided by N. So an example of a blue edges is 3, 5, which is not red, not present in G prime. And with the remaining probability, you put no edges. So again, you have two parameters to remember: lambda, which is a positive parameter, and S, which tells you how correlated the two graphs are. So when S is close to 1, the two graphs are very correlated. The intersection of G and G prime contain most of the edges. And when S is close to 0, then this is the opposite. You basically have two independent Erdős-Rényi random graphs. So now what we do is, I said I'm erasing the indices in G prime. So here, more formally, what I'm doing is I'm taking a permutation uniformly at random, which will be called pi star in my talk. And I'm relabeling the vertex of G prime in order to obtain the graph H. So here I did not modify G, and on the left and on the right, you see H, which is a permuted version of the red graph G prime. Of course, if you look at G or H in isolation, so the marginals, they are standard Erdős-Rényi random graphs with average degree lambda. So this is why I'm taking this scaling. I'm divided by n, the number of nodes. And the goal is, given these two graphs, G and H, try to recover the permutation P star. So first, a few results that were already known in the literature. I wrote mainly the exact recovery of P star. So you can write the joint distribution of G and G prime, so without the permutation, to see that it depends mainly. So there is a factor depending on the parameter of the problem, lambda and S, and to the power this, which is a short notation for the number of edges which are both in G and G prime, so the edges with two colors. So you see from this simple observation, you see that the map estimator of pi star. So if you want to recover the whole permutation, you need to basically maximize the number of common edges in G and H, where H is obtained after applying the permutation P star to G prime. And this is exactly the problem of the quadratic assignment problem, where A and B, the matrices here, are the adjacency matrix of the two graphs G and H. So it's NP-hard problem, but you can ask when the solution of this problem gives you the exactly pi star. And so there has been work showing that you need an average degree scaling with the number of nodes, so tending to infinity, at least faster than log n, in order to be able to recover the pi star. And there are even more recent results. I think Shengmao will speak about a very recent result on this problem tomorrow. When the noise, the 1 minus s, remember s is the correlation, so 1 minus s corresponds to the noise. When the noise is small enough, then you have polynomial time algorithm in order to recover pi star. So in this talk, I will not be interested in this not very sparse regime. I will only consider the very sparse regime where the average degree lambda, so my parameter, is not scaling with n. So this is a fixed parameter, let's say 3, and you want to get a result for this problem. So of course, now you will not be able to recover a pi star. You will have isolated vertices, and it's clear that recovering pi star is not something meaningful. So you need to modify the notion of performance in order to get interesting mathematical results. So this is what we call the planted graph alignment problem. And we define two measures of performance. The first one is called the overlap. Those is defined by this. Basically, now since we know we are not able to recover the whole pi star, we'll try to recover marginal of pi star, so prediction the pi star of I. Okay, so from if you want a block maximum a priori, now you want what people call in decoding a symbol map estimate for each marginal of the permutation pi star. So here you are counting the number of good guesses made by your estimator, and you see that now, since you are not asking to recover a permutation, we are even relaxing the fact that sigma hat does not need to be a permutation; it can be a partial matching. And indeed, you are allowed to only give a prediction for a subset of the node, which is denoted by C here. But still, you are divided by 1 over n here. Okay. So this is the first notion, overlap. And then there is another notion we will play with, which is called the error fraction of your estimator. And given by this formula, this is basically the number of wrong guesses you are making, again, on your subset C. And now we are ready to define the notion of performance we will study in this work. So we let n tends to infinity to get asymptotic result. And we want probability tending to 1. And so partial recovery means that the overlap is positive with probability tending to 1. So in particular, you see that the subset C need to be at least a fraction of the nodes, and you need to make a good guess on this positive fraction of nodes. And we'll look at something more, which we call one-sided partial recovery, which in addition to this partial recovery, we want the error to be small, little more of 1 when n tends to infinity with probability tending to 1. So this means that in C, the fraction of error is vanishing. So I hope so. This will be the notion of performance in order to study our algorithm. Is there any question on this, or is that clear? Okay, so I will go on. So I will
maybe a quick clarification. So
yeah.
the set C need not to be the full set of nodes from 1 to n?
Yes, exactly. So this C here is the same C as we are summing here. But you see that as soon as you are asking for partial recovery, you want the subset C to contain at least a fraction of the node. When n tends to infinity, it cannot be a vanishing number of nodes.
So in the end, the choice of C is part of the algorithm too? So it will be random?
Yes.
Yeah, okay, cool.
Yes.
Thank you.
Thanks. Any other? Okay. So now that we switch the problem from a block estimation of the whole permutation to only the marginal, we can try to consider what we could call a local algorithm. So I put parentheses here because there is a formal definition of what local algorithm is. On here, since we are playing with two graphs, it's not exactly this one. So you have your graph G on the left, on the graph H on the right. I'm taking one particular node in G, and you have to find a good candidate for pi star of I in the graph H on the right. So one way to natural way to do is to consider the local neighborhood of I, so my original graph in G, and give any a candidate for the match pair on H, and you will go to a finite depth, and this is why we call it a local algorithm. So you want to make a decision on the score if you want to match the node I on the candidate U only based on the local information around I in G and around U in H. So as you know, the local neighborhood in both graphs will be trees in the large n limit in the regime of I'm considering the average degree again is fixed. So this will be a Galton-Watson tree. So this is why I depicted here. I'm taking the root, my vertex I on the left, on the tree T prime on the right, the root is a candidate for the matching pair of I in H. So these are not exactly the same tree. And actually, Lucas and Laurent derive an algorithm which was presented in a paper last year, where in order to get a score between the node I and the node U, they were looking at the largest common subtree, which is common on the left and on the right. So this is what is called the matching weight. So here, with Lucas and Laurent, what we did, we modified this to something which is a little bit thinner. We look at hypothesis testing in this for these two graphs. So what is the hypothesis testing problem here is you're asking, are these two graphs in some way correlated or not? And if they are correlated, then they are likely to be matched in the original graphs because they have common pair. And what we want to compute is exactly the probability for these two graphs to be correlated. So now you see that I did transform my original problem on a graphs into a problem on trees. And I will be a little bit more formal here. So I will be a little bit sketchy in the way you define the probabilistic model for these both for the couple of tree T and T prime, but you can have a look at the details in the paper. So clearly the marginal again are Galton-Watson branching process with offspring lambda. But if I and U are correspond to the same, so U is actually a P star of I, then the two trees are correlated with the parameter S. So this is what is written here. There is a common subtree with offspring, which is lambda times S. Okay, so this is in the case where U corresponds to the match pair of I. And of course, if U is not, then they behave like independent Galton-Watson trees. Now, the hypothesis testing problem is, can you test P1, so corresponding to the first model, where you have two Galton-Watson trees which are correlated thanks to this intersection of string with parameter lambda S. So this is P1. Can you test P1 against P0, where P0 is just simply the null hypothesis is when you have two Galton-Watson trees which are independent with a good marginal Poisson lambda. So, and again, here the D is a depth, and we'll go to a finite depth in the graph, or now a finite depth in your Galton-Watson trees. So it turns out that you can use the recursive structure, the branching property of your trees, and compute exactly the likelihood ratio between T and T prime. So this is the ratio of the probability under model 1 divided by the probability under the null hypothesis. And it verifies a relatively simple recursion written here. So I will pause a little bit. So again, D is the depth at which you are looking in your tree, both in T and T prime. So here you see that the likelihood ratio at depth D is a function of the likelihood ratio at depth D minus 1. This is the recursion. So you can compute them starting from 0 to D. And this is exactly what our algorithm will do. Now you have first a combinatorial term here depending. Those C and C prime are the number of children of the roots of T and the root of T prime, respectively. This is a combinatorial number coming from the Poisson distribution of the degree. So it's written here. And here you have actually a huge sum where you are summing over all k, where k is varying between 0 and the minimum of the two offspring. And you see you have a product of likelihood ratio at depth D minus 1 between the subtrees in your original tree T and T prime. So here I try to give an example of this term, okay, for k equals to 2. So let's say that C is equal to 3, so the root in T has alpha, beta, gamma as children, and in T prime it has 4 children, 1, 2, 3, 4. So if I want to compute this term for k equals to 2, here what I'm doing is I'm fixing, I'm taking 2 children of the root on the left, let's say alpha and beta, and I'm matching in, I need to match them to children of the root on the right. So the first term will be when I'm matching alpha with 1 and beta with 2. And then I'm matching alpha with 1 and beta with 3, alpha with 1, beta with 4, this term. And you need to do it for all pair of vertices on the left and pair of vertices on the right. So this is already for k equals 2, you see that you have a huge number of terms coming here. So from a practical point of view, since I mean this is what we will compute in the algorithm in order to get a score for these two vertex to correspond to be matched. You see that here, when the average degree is high, this sum, you will have a factorial of the degree number of terms. So it will not be doable in practice. But from a theoretical point of view, what you need to do in order to solve the hypothesis problem for tree is to understand this recursion. All the information is contained here. So this is what is written on this slide. So since I'm asking for both good overlap and a low error, I'm considering a one-sided test where you see that I don't want, if I'm under the null hypothesis, since I will have a lot of pairs corresponding to, of course, there are a lot of pairs corresponding to the null hypothesis. I don't want to make mistake at all here. So this probability should be very close to 1. And when I'm finding the right pair, I want to have a positive probability to get the right answer. So this is, you have vanishing type 1 error and non-vanishing power. This is why we are considering overlap on errors. And now, so in the paper, we prove this theorem, and indeed there are more equivalent conditions for the existence of such a one-sided test in the tree problem. So here, this set XD that I did not define here are the set of tree at depth D. So this is only a result dealing with trees, Galton-Watson correlated trees. And so there exists a one-sided test for deciding P0 versus P1 if and only if the Kyle divergence between P1 and P0 tends to infinity, and lambda S is bigger than 1. Or this, I did put also this condition because this is the one we will be using in the algorithm, at least in the theoretical analysis of the algorithm. So when LD is diverging, so we'll fix a threshold on, based on this threshold, we'll say whether the two nodes are matched or not. So there is also a small trick with, there is a small problem, technical problem with this, but I will not discuss it more here. If you have, by the way, if you have a very technical question, I think Luca is in the audience and will be able to answer. So this is the result for the hypothesis testing on trees, and now you can translate.
There's a question from the audience.
Sure. Oops.
There's a quick question about what is px?
Okay, sorry. Px is a probability of extinction for a Galton-Watson tree with the parameter lambda s. Thank you.
Okay, thank you.
So now here I did rewrite the notion of performance we are looking. So again, we want a positive overlap and vanishing error, which correspond exactly to this one-sided test. Positive overlap and vanishing error. And for given parameter lambda on S, n will tend to infinity, we can show that if one-sided correlation detection is feasible, so if you satisfy one of the conditions of previous theorem, then you have a one-sided partial recovery, so for the graph model. So this is the Erdős-Rényi correlated Erdős-Rényi model with parameter n, lambda, and S. And you can, the algorithm is basically the one I showed you before. The only part I did not specify is how you choose when you match I on a given vertex, and this is based on a thresholding thanks to this of the likelihood ratio you are computing locally, thanks to this result. And you can show that this algorithm is indeed polynomial in time, even with the huge sum which is present here, since the degree are fixed, the average degree is fixed, the maximum degree is not scaling too fast, and you can show that you end up with a polynomial number of computation. So now you need to find to translate basically this theorem in a range of parameters for lambda on S in order to satisfy one of these conditions. And as I said, there are even more equivalent conditions in the paper. And in order to do this, you need to come back to basically all the information is contained here. So you need to work on this recursion in order to translate it in a meaningful region of the parameter lambda on S, for which you can show that basically LD is diverging to plus infinity, or the KL divergent, which is the expectation of the log likelihood, is diverging. And this is what we have done, so mainly Lucas and Laurent. And here I will present you only the result in a form of a cartoon, because I mean, if the details are in the paper and the formula are not very insightful. So, but first, so we had a previous result where it's relatively easy to show that when lambda S is less than 1, so basically when the Galton-Watson tree corresponding at the intersection of the two graphs is dying, then it's impossible to do partial recovery. There is another result by probably people in the audience showing that when lambda S is bigger than 4, then it's feasible. So here I'm writing IT for information theoretically feasible, because they are not looking at being able to solve the problem in polynomial time. And so what we add is we found sufficient conditions for the existence of one-sided test. So we use two different techniques giving two different bounds, which correspond to the green part here, which we call easy phase, because as soon as you know a one-sided test exists, you know that there is a polynomial time algorithm working in this regime. So the two techniques are based on Kullback-Leibler divergence or the number of automorphisms of the Galton-Watson tree. And there is an additional result. We show that when lambda square is less than 1, so below this third curve, and when lambda is big enough, then basically the Kullback-Leibler divergence is bounded. So remember that if it's bounded, then we know that there is no one-sided test. So in this regime, basically our local algorithm will not work. And what we conjecture is that no local algorithm will work, although we do not have a mathematical statement of this. And probably you need more than local information to be able to recover, to have a positive overlap. And the interesting thing is that you see that the curve given lambda s equal 4 and lambda s squared equal 1 is crossing. So there is a regime where we know it's feasible, and it's probably not feasible in polynomial time. So this is what we call the hard phase, and we don't know exactly if the exact shape of this phase. this is why I'm drawing this cartoon. Is there any question on this part?
Can I maybe ask a clarifying question? So to go from tree detection to partial alignment, suppose you know U is in the second graph is the immediate children of I. Then these two trees, when they grow, they also will tend to have some overlaps, not following under the independent null model. Right? So how did you deal with this?
So this is a part I did not cover exactly. So this is here I did just specify how you compute the likelihood ratio LD, and what you are saying is
no, that's not my question. Is
but so
okay.
If U is a children of the right match, then the score will be high too for you, and you do so you might make a mistake on match I with the children. This is what you are saying, if I understand correctly.
Okay.
So what we are doing is we are using something that actually Luca and Laurent already did in the matching weight case, dangling tree trick. So in order to match two nodes, they need to have three children with a high score. And you can show that this will avoid the problem you are referring to.
These will actually distinguish, children versus itself.
Yes.
I see. Okay. So it's not straightforwardly applying the test statistics to the two local neighborhood. It's more involved.
Yes,
okay.
There is a trick. Yes, exactly.
Thank you.
Thanks for the question.
One more related question is, so I guess this means that you're only matching nodes that have, I guess, degree at least 3, but is there some further maybe characterization of what set of nodes are those that you match, what kind of properties they have?
I'm not sure I understand the question.
In this way, you match a subset of the nodes, right?
Yes.
And this is a correct match.
Yes.
And so is there some characterization of which nodes are those that are matched based on some, I don't know, graph properties?
Essentially this set C.
The set
yes.
C. Yeah.
So this is what you are trying to say is what can I say about the set C?
Right. So the set C will be some set of nodes, and those will have some kind of, I guess, graph properties. Maybe is there any way that those could be described?
Okay, so they will all have degree 3 because of this. What I just say, you need to have 3 children.
At least 3. Yeah.
Yes.
Yeah.
And the score for the 3 children need to be high in terms of likelihood. So okay, I mean, so this is for the theoretical part of the algorithm. And when we did implement the algorithm, of course, we did not implement this because already requiring to have a degree 3 in a very sparse graph will kill a lot of nodes. And so from a practical point of view, this is kind of annoying to do this. But in order to get a theoretical algorithm achieving the performance we claim, you need to do that.
Thank you.
So in the last few minutes, I don't know, I will speak about a completely different approach to this problem, which is based on learning. It turned out that for this problem, it's very easy to get a data set of graphs with the right label. The thing you do is you take one graph, you take a random permutation, you attempt G2, and since you picked the permutation, you exactly know what you need to recover. So what we try with Waze is to learn an algorithm which will learn a representation of the graph, mainly of the nodes. So this is what I'm calling the FGNN here. It's taking as input a graph G1 and producing, you see, a vector of size D living on the vertices. And basically, this embedding of the nodes should contain the relevant information around each node. And now you are playing the same algorithm here at the bottom on G2. You obtain embedding for the nodes, and you obtain a similarity matrix by taking the dot product of the embedding of your nodes in graph 1 and graph 2. Okay, so this is a square matrix, and you want to have a high score in this similarity matrix when the two nodes are matching each other. And since I did choose a permutation at the beginning, you can learn the way you are building an embedding here in order to get a similarity matrix, which is meaningful at the end. So this is what we did. So there is one thing which is a little bit tricky in this approach is you want this algorithm mapping a graph to vertices of node to, of course, capture the symmetry of the graph G1. Namely, if you permutate G1, you want to permutate the output. So this is what people call equivariant function. So here is a definition I'm looking now at graphs as a adjacency matrix, or if you prefer, tensor of order 2. And the action of the symmetric group is given by the standard permutation of line and column. So this is just to define the notation star. And a function, so taking as input a graph and producing an embedding of nodes, is said to be equivariant if when I'm permuting my original graph, so permuting the row and column, so basically relabeling the nodes, I will obtain a permuted version of the labeling. So this is a graph neural network we use as this function need to be equivariant in our case, and we show with ways that we use FGNN, which has the best power of approximation among all architecture working with tensor of order 2. So I will not speak about that here. I want just to describe shortly the main graph layer we are using. So this can be seen again as a message passing algorithm. But here, the main difference with the standard message passing algorithm is you are passing messages with all pairs of vertices. So here, I and G need not be connected. I and K here need not be connected. So you are building an embedding, if you want, of all the pair of vertices. And based on this, you are building the next embedding and so on. So if you prefer, you are looking at the complete graph on the n vertices. So I wanted to say this because you see here that the way you are building the embedding is not at all local anymore, since you are looking at all the pair of vertices. So the question is, can you learn a good embedding with such a technique? And so this is a experimental result. So we have no theory at all about on this part. So we did train our network on the Erdős-Rényi correlated model, and we compare to other SDP relaxation or spectral method in GRID for Erdős-Rényi and also for correlated regular graph model. So of course here you can run the algorithm on any kind of graphs. You are not restricted to Erdős-Rényi. And the nice thing is plotted here. Probably it turns out that the algorithm is generalizing very well. So here on each line, you have a different model trained at a given level of noise. Okay, so the noise is 1 minus s in my notation. So each line corresponds, but you are running the algorithm so at test time for all different level of noise. So you are training, for example, this line at a noise 0.1, and then you are trying to see whether it's performing well also for different level of noise on which it was not trained. And you see that it's relatively flat. And actually, this algorithm turned out to be the best one, achieving the best performance at all level of noise. So which means that in order to get a good performance, you don't even need to know the noise parameter in your model. And just training at one level of noise will give you good performances at the other level of noise. So this is a comparison of the performance of the two algorithms. So the local one, which is called BP here, but I think probably it's a misleading name. So this is a local algorithm based on the local neighborhood. So without the downlink trick, because otherwise the performance would be very bad, because here I'm considering correlated Erdos-Renyi graph with average degree 3. So you see that if I'm removing all the nodes with degree less than 3, I will not keep a lot of them. And the number of nodes is 200. So it's not that huge. And the surprising thing is that the graph neural network is basically starting to detect signal at the same time as the local algorithm with a lower performance, but probably you can increase it. So this is rather surprising. The main advantage of the graph neural network is you can run it for a much larger degree, whereas for the practical reason I said, the local algorithm will, at least the exact version I just presented, will not run in a decent time if the average degree is too big, because there is a factorial times the degree basically in the computation time, so which is killing the performance. So here I did compare with the Grandpa algorithm. So in blue you have the Grandpa performance. So I'm using the same notion of noise as in their paper. So this is why now it's the accuracy is when sigma is close to 0 and so on. And this is for average degree 50. Okay, so you see it's a much denser network. And my algorithm, the graph neural network, is still performing very well in this case. And I train only once at a given noise in order to get all these results. But now I tried very recently, what will be the performance of my graph neural network for a lambda crossing what we believe to be the art phase. And so this is the result I obtained. So I took average degree 20. So this is somewhere over there, where you start to see the two curves crossing here. So you know that there is a phase where it's feasible, but not with our local algorithm. So the two dotted lines are here. So here this is the art phase, and it should, I mean, it's feasible on the right of the dotted black curves, and you see that the performance of the algorithm actually is need to be a much higher signal than this lambda s equal 4 in order to get a decent result. So we are even in this case, the GNN is not able to, will perform well only close to S equal 1 over there. So this is, I mean, this means there are perhaps still things to do, and I will end with this last slide with a reference to, I don't know if you've read this blog post from Rick Sutton on the beta lesson, who is basically saying that you should not spend time on smart algorithm as we do. In the end, AI will be able to outperform our algorithms thanks to Moore's law. So I don't. If you believe in this, you should probably work on GNN to solve the hard here. Thank you. I hope I was not too long. Do you have questions?
Thanks, Mark, for the great talk. Any more questions from the audience?
So I have one question. So here in the phase diagram, what's your reason for believing that there's the yellow region of the hard phase? Is that because the local tree test fails?
Yes, that's basically it. We know that below this curve for lambda, below this curve lambda s squared equal to 1 and lambda big enough, the one-sided test will fail.
Okay, thank you.
So this is the theoretical result, and then yeah.
Any more questions from the audience?
And sorry,
yeah,
and there is also in this orange phase. I mean, we know thanks to the result of I think I don't know Jiaming, Yiwong, and I don't remember the last author. That it's feasible, though probably by a non-local algorithm. So this is why we conjecture it's hard. So we know it's feasible for sure, and local algorithm will probably fail.
So this yellow region, the negative results is actually firm, applies to the failure of the tree testing.
Yes, exactly.
I see. Okay, thank you. Any more questions? Okay, if not, let's thank Mark again for the great talk.
Thank you.
So we'll reconvene in maybe 30 minutes. Okay.